In this video, we're going to learn about finding the operating point of actually fixed bias and self-bias JFET. And we're going to do it both. We're going to do it mathematically and we're going to do it graphically. And you're going to find out a lot of these examples, it's much easier to do it graphically than to do it mathematically, especially when it's self-biased. So let's take a circuit. Let's assume we have this circuit here. We have a VDD. I don't have to give you a number. We can use numbers for that. And this is the resistor to the drain, R sub D. This is your drain here. Source, drain. And now, this is the gate here. RG. And let's put a source here. We'll call it minus, plus, minus, plus. And that's attached to the ground. And let's give it a value. That's the minus, the plus. We'll call it VGG. And now, let's put some coupling capacitor. Let's say we have a capacitor here, and that's my input voltage, VI. But in this example, I'm going to be using DC source only. And let's put another coupling capacitor here, C, and that's V out. Now I know what V out is. Now, a few things here, why we call it fixed bias. You will see in a few minutes that the value of VGS does not change. I don't care what you put for a value for R sub G. Big or small doesn't make any difference. So that's where the name fixed came from. So again, with the source being DC source, that means your frequency is actually 0. If the frequency is 0, then the resistance of this one for the capacitor is going to be infinite. So the capacitor is going to behave as an infinite resistor. And if it's an infinite resistor, might as well just take them out. So this circuit actually will turn to this one, VDD, R sub D. This is V out here, which is V at the drain. The source. R sub G, minus, plus, minus, plus, and there's the ground. You can attach both grounds together if that's easier for you. Another thing about these JFET is you have the data sheet for each one, which means what? IDSS will always be given to you, and VP will always be given to you. That's the pinch-off voltage. So the VP here for this, let's assume it's 6 volts. And IDSS, let's say it's, I don't know, 10 milliamps. I'm just making numbers up. So these will be given in the problem. This is the gate here. This is the source. This voltage plus to minus VGS. Well, one thing we know about these JFET, that the current going through the gate, I sub D, is really in the nanosecond. So that's approximately 0. If that's approximately 0, when we calculate the voltage drop, it's going to be going up this way. If that's a 0, then the voltage here plus to minus, we'll call it the voltage cross that resistor using Ohm's law. It's 0, that's the current, times the resistor, which is R sub G, and that will tell me that's a 0 volt. I drew the plus minus backward here if it's going upward. That's 0 volt. So if we do Kirchhoff voltage law here, And again, it's really up to you, a plus to minus, if you want to call that minus or a plus. Most people call that minus. I tend to call them plus. So plus to minus, that's plus VGS. Plus to minus is plus VGG. Plus to minus is plus 0 is equal to 0. Kirchhoff voltage law. Sum of the voltage in a closed loop, that's a 0. Or if you do the math, that tells you VGS is equal to negative VGG. And we know that's a fixed number. That's a source there. That's why this circuit is called a fixed bias configuration, because VGS will always going to be, for this example, a fixed value. Now, if we know what VGS is, we can calculate what the current I sub D is. When we ask you for the Q point, the operating point, that's called Q point, where that transistor is going to be working at, we're looking for two numbers. We're looking for the voltage, which we called VGS Q at the Q point, and we're looking for the current at that point, IDQ. That's the X value, that's the Y value. That's what we're asking for when you say find the Q point or the operating point. So we know what the voltage here is, VGG or negative VGG. But what is ID here? Well, to find I sub D, what do? We go to our equation for the current, and we go I sub D is equal to I sub DSS times 1 minus VGS over, we used to write VGS of, or you can write negative VP here or plus VP, it depends if your VP is positive or negative, and you're going to square it. So that will give you the value of the current going through it. So your Q point here is going to be, for this example, it's going to be, remember, VGS is equal to negative VGG here, and VP is negative 6 volts here. So I'm going to write, it's 8 or 10, I use 10 milliamp times, so that's ID at the Q point here, we'll call it Q, is going to be 10 milliamp times 1 minus, this will be VGG divided by VP, which is the 6 volts, and you're going to square that. So if you tell me what is that value of the source there, I will tell you what that current is going to be. I can't really answer it till you tell me how big your source is. So the Q point of this actually circuit, again, the Q point here is going to be negative VGG, that's what VGS is, and the current is going to be, it's I sub DSS, I just leave it like this, 1 minus VGS over VP squared. So when this transistor is working, you tell me what this value is, I'll tell you what VGS is going to be, and I will tell you what I sub D is going to be. So these are the two answers for the Q point. And if you really want to find out what is VDS, the voltage between the drain and the source, I don't need it, but if you're looking for it, you know it's going to be that voltage drop, the voltage source there, excuse me, VDD minus the drop across that resistor, which is what? R sub D times I sub D. So the math here wasn't that big of a deal. Calculating these, you just, if I gave you some numbers, we can do that in 2 minutes. So here's an example. I'm not going to put the capacitor, I'm just going to eliminate the capacitor. Let's go back to this one. Let's put in some numbers. Doesn't matter what numbers you want to put in. So here we go. I'm going to put VDD equals 12 volts. R sub D, the resistor on the top. Let's give it a value of 3K. And let's put R sub G here, 10 meg. And let's put a voltage source minus plus minus plus. of negative to positive 5 volts. I'm using the same transistor. Let's assume I sub DSS here is equal to 10 milliamp. And let's assume VP, the pinch-off voltage, is really, it's a negative value, but a lot of times we don't give you the negative. We go 6 volts. But you want this end to be actually 6 volts lower than that end. We already just finished saying that the current going through this is going to be 0. So the current up there is 0, which means that resistor is useless. 0 times 10 meg, that's 0 drop. So VGS here is going to be negative 5 volts. And what's I sub D is going to be? I sub D is going to be I sub DSS, which is 10 milliamp, times 1 minus VGS, which is 5, over VP, which is 6, and you're going to square that number. Some of you going, how come you're going to write that minus 5? Well, if you're going to put this minus 5, you better make this minus 6. So now let's calculate that current. 5 over 6, 1 minus 5 over 6, that's 1 over 6. Square that, that's 1 over 36. The current I sub D is going to be 10 divided by 36 milliamp. So what is the Q point here? When this transistor is connected like this, it's going to operate at a voltage of negative 5 volts here, and the current I sub D is going to be 10 over 36 milliamp. Again, the mathematical approach for a fixed bias configuration, it's not really that difficult. But let me show you the graphical way of doing it. So we can do the math here. It's not a big deal. But when we get to the next one, it's going to be a big deal. So the graphical way of doing it, so this is the graphical approach. Of the same circuit. If you remember the current through the JFET, we said has this equation, I sub D equals I sub DSS 1 minus VGS over VP squared. So let's take 3 values here. Let's pick 3 values. What will happen to this current if VGS, this is case 1, if VGS equals to 0? What is 0 divided by VP? That's 0. 1 minus 0 is 0. 1 minus 0 is 1. Square it, that's still 1 times that number. I sub D is equal to what? I sub DSS. Case 2. What happens when VGS, let's choose VGS equals VP. What is VP over VP? 0. 1. Boy, I'm a mess this morning. 1. What's 1 minus 1? 0. Square it, that's 0. Times this, I sub D is equal to 0. So if I go to graph that, I don't have a ruler, let me get one. So I'm going to graph the current here. We graphed it in the previous video somewhere there. Don't remember where it was. 2 or 3 videos ago. This is VGS. And this is I sub D in milliamp, usually. When VGS is 0, we said I sub D is I sub DSS. So that's somewhere here. And when VGS equals VP, it's going to be a negative, because it's a negative number, really. The current is going to be 0. The question is, how quick is going to rise like this? Is it really steep or is it slow? That's a hard one to figure that. So to figure that, we need one more point. Now make the math easy for us. What happens if I pick VGS equals VP divided by 2, half of VP? When you put half of VP, when you divide it by VP, this number becomes a half. So I sub D is going to be I sub DSS. This will be a half. So what's 1 minus a half? That's 1/2. And we need to square it. And that will make it I sub DSS over 4. So if you divide this into 4 sectors, 4 equal spaces, so each one is going to be a little bit more than, so this is 1, this is 2, this is like 3 here. So a fourth, when it's right here, it's a fourth. And that's your third point. So the graph should look like this. This is I sub D, the graph of I sub D. Now, let's find out what I'm graphing VGS. Now, for VGS here, from the previous example, we're doing the same circuit, we said it was negative VGG. You tell me what VGG is. So, for example, if VGG was somewhere here, then this actually JFET is going to be operating at this point. That's your Q point, right there. So the current will be from the graph. In this case, it looks like half of I sub DSS. If VGS was right here, you draw a line going up, and that'll be your Q point. Oh, that's about 1/8 of the current going through it. So you give me the value of VGS between 0 and VP, between these two values, and I can tell you what that current from that picture. So that's a little bit much quicker to do it graphically than to do it mathematically. The advantage you're really going to see is in the next example. The math is going to be ugly. So let me take another one. And I'll attempt to do it mathematically. I might give up halfway through because it gets too ugly. So we're going to look at self-bias configuration. Of JFET. What's a self-bias? Well, let's look at that. VDD. Almost the same circuit now as before. I'm going to keep it identical with one little exception. And the exception is I'm going to put a resistor here. I'm going to call it R sub S because that's the source. The rest of the circuit going to stay exactly the same as before. Oh, I shouldn't say exactly the same. I'm taking that source out. So that's the other difference. This is the first coupling capacitor, and that's V input. This is the next coupling capacitor, and that's V out. So two things different here than the previous one. Let me put the previous one next to it so we can look at them. Here's the old one. You had two sources here. Now you only have one source. Only one power supply. For us, that's much better design. Now the other thing, the other difference that you see, there was no resistor here. Now we have a resistor here. How is that going to change the Q point, the operating point? Again, let's look at it in terms of a DC source. So DC source, that's what we have. That means all the capacitors will go away. They become open circuit. And my circuit will look like this. RS RG, and this is VGS right there. Gate, source, drain, and that's your V out right there, the drain. VGS. It should be a negative number. The same assumption as before. We're going to assume the current going through this is approximately 0. I sub gate is approximately 0. And if that's 0, there is no voltage drop here. Use KVL, Kirchhoff voltage law. It says plus VGS. Continue this way. The current's coming down. From up there is coming down, so it's going to mark it plus to minus. Plus R sub S times I sub D plus 0 times this, which is 0, is equal to 0. So VGS here is equal to what? R sub negative R sub S times I sub D. So I'm looking for the Q point here. When this JFET is working, what is the voltage and what's the current? You can see the voltage, it's not a fixed number. VGS, it depends on I sub D. If I sub D is larger, this is larger. If I sub D is smaller, that's smaller. So it's going to be at VGSQ, that's the operating point, and the current I sub D is we're going to call it I sub DQ. We're looking for these guys. Now, same as before, I sub D, if you recall, is IDSS, which usually given to us in the problem, times 1 minus VGS over VP, and VP is also given to us in the problem, squared. So let's do that substitution. I just finished saying that VGS is equal to this. Well, go to that equation and replace VGS with this value. So this becomes I sub D equals I sub DSS again, we call it I sub DSS. Why? It's the current between the drain and the source when this end is short-circuited. That means this value is attached right there, short-circuited. That's the maximum current you're going to have, is equal to 1, and since that's a negative, what's minus a minus will make it a plus. R sub S, I sub D over VP, and you got to square that. Oops. And now the math gets really ugly, because you want to solve for I sub D. You can't solve for I sub D if you have I sub D here and you got I sub D there. You need to isolate them. Well, how do you isolate them? Well, the only thing you can do right now is FOIL this one out. And if you FOIL this one out, it's the first one squared. And by the way, if you don't like the way that's looking, you can complete the square first. I'm not complete the square. Find the LCD and write that VP plus R sub S, I sub D, because that might make the math a little bit easier. And I can square this and square the top and rewrite that as I sub dss over VP squared times VP plus R sub S I sub D squared. So I squared this one, squared that one, but I pulled this one outside. And sometimes I wonder why I go through the math. This is not going to be pretty. Foil this one out. And that becomes VP squared plus R sub S squared I sub D squared plus 2 times VP RS ID. The FOIL, that's A plus B squared. What I used is this rule. It's A squared plus B squared plus 2AB. And if you multiply, distribute that one, this times that, the VPs will cancel the square. You end up with I sub DSS plus, if you multiply this by that, you'll have I sub DSS RS squared ID squared over VP squared. And if you multiply this by this, one of the VPs will cancel. It'll be what? 2 times I sub DSS times RS over VP I sub D equals I sub D. Now I'm looking for I sub D. That means I can't leave it here. I got to move it to that side and make it a 0 here. And maybe I'll attempt to clean this a little bit. I'm going to write that I sub DSS RS squared over VP squared, all of that times I sub D squared. When I move this to that side, that becomes a minus. 2 I sub DSS RS over VP minus 1, because this one's going there, becomes a minus 1, times I sub D plus I sub DSS. The reason I'm writing this way, because I'm trying to solve for I sub D. This is a constant, that's a constant, this is a constant. So this is some constant, we'll call it K1. Constant, 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 constant. All of these are constant. That's K2 I sub D. And that's also a constant. So if we know what these numbers are, if I gave you some numbers for them, this becomes a quadratic equation. And we can solve for I sub D. And you're going to have 2 values, because that's quadratic. One is going to be a good value. One is going to be a bad value, and we're going to choose the good value. Since I didn't give you any numbers, you can't really solve it. The point I'm trying to make here, it is ugly to do this problem mathematically. So how do we do it then graphically? Graphically will take me 2 minutes to do it. Let's look and see. So we're going to do it the graphical approach again. And for this problem, I'll be doing the graphical approach all the time. We know what the current is. We talked about that in the previous, well, in the same video 2 minutes ago. So if you rewind that video back maybe a third of the way, you will see I have 3 points. When VGS equals to 0, I sub D was what? I sub DSS. And when VGS was VP, I sub D was equal to 0. And when VGS was VP over 2, I sub D was I sub DSS over 4. So these are my 3 points I'm always going to graph to find my current, or the graph of it. I sub D versus VGS. 3 points, I sub DSS, VP here, or negative VP, and halfway between, that's right there, halfway between this and that, and this is going to be a fourth of the height. A fourth, it looks like somewhere here. And that's my third point. So this is my I sub D versus VGS. Now I need to find the equation for VGS. Let me go back to 2 pages ago in my notes, maybe 1 page, no, 2 pages back. And I wrote this one. VGS equals negative R sub S I sub D. Now, if you look at this graph here, VGS is really your x-axis, and I sub D is your what? Your y-axis. So if you want to solve that, when you have an equation that looks like this, x equals k times y, and I say solve it, you'll say y equals what? X over k. Well, if we do that here, that tells me in this equation that I sub D is equal to negative 1 over R sub S times VGS. This is a straight line. So I need 2 points to graph it. Just 2 points. Point number 1, we'll call it A. I don't want to call it 1 and 2, that's for this one. I'll call them A and B. If VGS is equal to 0, what's I sub D? From this equation, equals to 0. That's 1 point. Point number 2, pick any number that you want to. So I want to make the math cancel out. So what about if I pick VGS equals negative, because it has to be on the negative side here, I sub DSS over 2R sub S. The reason I picked that because I want the R sub S to cancel each other out. So if you plug it in, so let's do the math here. Negative 1 over R sub S times negative I sub DSS over 2R sub S I should say times R sub S to cancel the R sub S. That'd be a better choice. R sub S here. Notice what happens. The R sub S cancels the R sub S. That was my goal. And the minus cancels the minus. That means I'm going to have I sub DSS over 2. So that's half of that here, somewhere here. And I don't know, I have no idea where that point is physically because I don't know what that number is unless I pick numbers, you know. But let's say the number was right there. This value for VGS was right there. Let's assume that's the case. That gives me my second point, and I'm going to draw my line going through that from this to that, and here's my Q point. So we will have this much current going through it, and we'll have that voltage at that time, which is right there, that number. And that's much easier, especially if I gave you some numbers in this example. So let me give you some numbers quickly for it, just to show you how much easier. Let's assume I sub DSS here equals 8 milliamp. Let's assume VP equals negative 4 volts. And let's assume R sub S, I don't know, equals 400 ohms. So my operating point here is going to be what? This is VGS. This is I sub D. At 0 is going to be 8 milliamp. At negative 4 here is going to be 0 milliamp. Halfway through that at negative 2 is going to be a quarter of that number, 2 milliamp, a quarter somewhere here. So right there. So my graph will look like this. I sub D. Now let's go and graph that equation here. When it's 0, it's 0. In my next value, let me pick these numbers here. I'm using VGS equals to what? Negative, the example I use, I sub DSS, which is what? 8 milliamp over 2 times, what did I use for R sub S? 400. So let's do the math. Negative 8 EE to the negative 3 times 400 divided by 2, I get negative 1.6. If I use that according to my equation here, I sub D is going to be what? I sub DSS over 2, which is what? 8 milliamp divided by 2, which is 4 milliamp. So I'm done. My next point is negative 1.6. That's right here. Let me draw a negative 1.6, a line going way up there. And the current is going to be 4. 4 is probably right somewhere here, halfway between. Let's say it's right there. I don't know. Not sure exactly where the 4 is. So that's that line here. So my line now is going to go straight like this. And here's my Q point. So at this voltage is negative 1.6 volts. My current is going to be that number. This is the 4 milliamp. This is the 2 milliamp. So somewhere between, more than 3, between 3 and 4, that's what my current is going to be. So when, with this circuit, with these numbers I'm using there, when this JFET is running at negative 1.6 volts, my current is going to be that number. And that's much faster and easier way to do actually the Q point.